Okay, so we're going to be talking about chapter 3, atomic. So the atom. Did we first hear about the atom? Well, there was a fellow called Democritus. He lived in Greece. He was a philosopher and realized that he took a seashell and took a pick and broke it into tiny pieces, breaking it. At some point, you could not cut it anymore. And the word atomos became the word for something that you cannot cut anymore. And from that Greek word, we get the term atom. Of Democritus, he was known as the laughing philosopher, a jovial fellow. And again, 300 years before Common Era, so almost 2,500 years ago. There's some basic laws of atoms. We've all learned about the law of conservation of matter or mass in other classes, and of course it tells us you can't create or destroy any matter. For example, if you have sugar, you put it in water and it dissolves. It hasn't disappeared. The total solution should have the same mass as the two components, water and the sugar did. You haven't created or destroyed anything. It's a basic principle. Another example would be if we tried to look at a chemical reaction equation. This is a reaction equation for ethane reacting with oxygen in a combustion reaction or a burning reaction and forming carbon dioxide and water. But in the first case, we can see that carbon is represented in the ethane, C2, but on this side, there's only one carbon, invisible one right here. So this is not showing the conservation of mass because there's more carbon on the left than there is carbon on the right. And you could check the other atoms and you'd see the same thing. So we use these red numbers as coefficients to balance the equation. These are multipliers. So now we have two carbons in a molecule that has two carbons. That means a total of 4 carbons on the left. And if we come over here on the right side, the product side, we see a 4 in front of CO2, and that means there's 4 carbons on this side. And we could look at every atom and see that that works. That is called the conservation of mass. Okay, well, there's another law that says we have definite proportions or definite ratios when there is a compound that we know. For example, at the bottom it explains the compound called salt, NaCl, sodium chloride. Well, you can see by looking at this that there's one sodium and one chlorine in this in this molecule. And if you were to weigh this molecule and separate the sodium and the chlorine, you could prove that there's 39% of the mass is due to sodium and 61% of the mass is due to chlorine. Turns out if you look at the periodic table, the mass of chlorine is quite a bit heavier than the mass of sodium. So that sort of makes sense. Even though there's a 1-to-1 ratio of atom to atom, the mass ratio is different. And every time we have salt, we will see the same mass ratio. There is a definite proportion in a compound. Another law is the law of multiple proportions. It states that different compounds can be formed combining the same elements in different ratios. And at the bottom, I've given a couple of examples. H2O is water. H2O2 is hydrogen peroxide. We can water. Hydrogen peroxide is what we use on cuts. It usually comes in a brown bottle, and if we put it on dab it on a scratch or a cut, it will bubble as it's cleaning the cut. CO versus CO2, carbon monoxide versus carbon dioxide. Carbon dioxide is a gas. It's rather harmless. In fact, it's what makes the bubbles in your soft drink that you may have, that you may enjoy. Whereas CO, in a different ratio, 1 carbon to 1 oxygen, carbon monoxide is a poisonous gas. It comes from the incomplete burning or incomplete combustion of a carbon-containing compound. So just changing the subscripts changes one compound to another. And in fact, there's a joke where a man walks into a bar and says, "I would like some H2O." And he's given a glass of water. And his friend walks up to the bar and says, "I would like some H2O too." And he dies. Why is that? Because water we can drink, hydrogen peroxide would kill us. Let's look at the people who discovered the atom. I like to call them the old dudes, the old atomic dudes. And there are some major players in this timeline of events. You've all created a timeline and looked at the different scientists, but maybe you picked some different ones than what I will go over here. The ones I will go over in this presentation are important, and you need to know these as well as their contributions, their experiments, their models. So first of all, we have John Dalton. John Dalton was a very smart man, and usually people who were very smart worked as teachers. So in 1803, he proposed a theory. He collected a number of bits of evidence that you can't collect bits of evidence that could be summarized in a theory. And that tried to explain and compile a list of these basic laws. Here's a picture of John Dalton. And if you look at what he's wearing and think of the year I just said, it was 1803, then John Dalton sort of appears to be dressed like some of the early portraits of our presidents. He was in that same era when our country was in its infancy, and he would have been in England. So what did Dalton's atomic theory say? It says that, 1, all elements are composed of tiny particles called atoms. And you notice that's that root word of the Greek word Democritus gave us. 2, atoms cannot be subdivided, in other words, taken apart. They cannot be created. They cannot be destroyed. We'll learn later that that was a good assumption, but number 2 there has been disproven. Number 3, atoms of the same element are exactly alike. If you have one atom of gold, it should look like another atom of gold. It should have similar properties, it should have a similar mass, and it should be the same size. That is true as a generalization, but we will learn that there are exceptions to point 3 as well. Point 4 says that atoms of different elements combine in simple whole number ratios to form compounds. And we'll look at those compounds similar to the ones we saw on a previous slide. The element name, the element symbol, always has a whole after it, or no number, which means it's a 1. You never see carbon 1, oxygen 1.3. It's always whole numbers. Well, Dalton helped to create a law, the law of conservation of matter. So the theory would change about the atomic structure little by little, but his law still holds. And he says that in chemical reactions, all it is we're combining, which means adding, separating, which means subtracting, or rearranging atoms. In a chemical reaction, no atom will suddenly appear in the products that wasn't part of the initial reactants. So conservation of matter just says we have to find all the atoms on the left side of a chemical equation as we find on the right side of the chemical equation. And he believed that an atom was just a small ball of matter and with nothing inside. So his model would look like this, a sphere, and it would be unable to be broken apart. You can't destroy it, and all elements have the same atom. They would be identical. If they're the same element, it would have exactly the same atom. Well, J.J. Thomson, Joseph John Thomson is the first one that disproved this. He was a British physicist, someone who studied physics, and he proposed a model that he called the plum pudding model. It was almost 100 years later. He discovered the electron, and he believed that the atom was a sphere that had a positive charge all throughout the sphere, but little electrons were stuck around in the sphere carrying negative charges. And together, those positives and negatives equaled a neutral atom. Here's a picture of J.J. Thomson. You can see by his clothing, we're approaching the 19th, 20th century, early in that time, and he was, again, a British scientist. So how did he do this? Well, in 1897, he was doing experiments using a cathode ray tube. Cathode rays are let me see, here's a picture, yep, a glass tube that can have gas inside of it. It's sealed here, and the air has been removed, so there's just some sort of gas inside. And if you put a battery or some sort of electrical source to give us voltage, then electricity will run through this wire and through the tube. Well, when it's inside the glass tube, the gas that's inside of the tube becomes excited. The gas suddenly makes a beam of light that will travel from this part of the wire through the tube to this part of the wire. And that beam of light, he discovered, had certain properties. If you put a magnet next to it, you can make the beam of light move and deflect. So he discovered if I put the negative side of the magnet next to the beam of light bends away from the negative magnet, meaning that the beam of light is repelled by something negative. If you turn the magnet the opposite direction and put the positive portion of the magnet next to it, he noticed that the beam of light bent toward the magnet. So the beam of light was attracted toward something positive. Since opposites attract and like things repel, he concluded that the beam of light must be negatively charged particles. So he called those electrons, since he discovered them using electricity. So negatively charged particles, electrons. J.J. Thomson was the first one to disprove Dalton's original theory. And he didn't measure the mass of the electron, but he measured something called the ratio of the charge of the electron to its mass. Someone later would discover the actual mass of the electron. So his model was a ball, again, a sphere, with a positive charge throughout it. All these little positives are to show that everything shown green on that model is positive. But the little circles with the negative signs in them, those were points of negative charge. So I want you to picture a pepperoni pizza. And the whole pizza, all the cheese and the sauce is positive. And then there are little points of negative charge on the pepperonis. Some people picture a chocolate chip cookie the same way. He called it the plum pudding model because that was a popular dessert in England that had little specks throughout it. And it was easy for them to visualize this model. So he's the first one who changed Dalton's theory, and he proved that there had to be something smaller inside the atom, so they were actually divisible, not indivisible. He proved that electrons were inside the atom, and that meant they were smaller than the atom.